engineering high-temperature materials.
Right.
So in particular, we work with ultra-high-temperature ceramics, composites, and coatings. So these were very early preliminary results, and we have other samples that have shown even better oxidation protection for the carbon-carbon substrate that we're currently working on, and we're going to be testing at the National Solar Thermal Test Facility at Sandia Labs. For me, as an outside researcher in a non-government lab, this test sample would cost me more than $40,000 to test.
Pour it in the dye, but a lot goes into making this powder before we actually fill it into the dye. So right now we're aligning the dye punch assembly with the powder in it so that it makes contact with the spacers and then the electrode.
This is what's inside the furnace right now, and so these punches are going to get really bright, and then this will start to warm up, and then this will obviously get as bright as the punches. The type of furnace we have in our laboratory is, it's called a spark plasma sintering furnace, and it is unique in the sense that conventional ceramic processing uses a furnace that heats up the material from the outside. So if your sample sitting inside and the radiant heating basically heats the material. The difference between our furnace is that it's rather novel to the field of ceramic processing still in 2010, because what it does is it uses a DC current that pulses through the material and consolidates it in a matter of minutes. So the advantage of spark plasma sintering is that we can basically retain that structure instantly and limit all of these grain growth that you would see in a conventionally processed ceramic.
Hello guys, welcome to our segment. We, students from the Advanced Material Department, will explain to you guys on the ultra high temperature materials. But today we would like to just focusing on the ceramic, because ceramic are the most material that have higher melting point among the others, which is this ceramic can withstand any temperature above 2700 Kelvin. Let's go.
In general, ultra-high temperature materials are the materials with melting points ranges from 2700 Kelvin to 5000 Kelvin. Thus, beyond that is super high temperature materials. For ultra-high temperature ceramic, which is UHTCs, are a class of materials that can be used in environments that exhibit extremes in temperature, chemical reactivity, erosive attack, and so on. Extreme environments could be considered as being encountered in applications such as hypersonic flight, scramjet propulsion, rocket propulsion, and atmospheric re-entry.
Okay, then we go for the classification of materials on ultra high temperature materials. The first one is carbon. The example of carbon is graphene and graphite. Then the second one is metals. That is tungsten and rhenium. And then we got composite. The example is CMC, or also known as ceramic matrix composite. And last but not least is our ceramic, the one that we are focusing today. And the example of ceramic is borite and carbide.
Have you ever heard about advanced material?
Advanced material. Previous semester ago, I have learned subject material science, which is cover only about conductor, insulator, and a little bit about polymer. But for me, the subject is only touch a basic one, not a detailed one. So you asked me about advanced material, so I think it is a depth about that subject, and it's maybe lah, maybe contain more about technologies right now, this year, maybe future, and technologies and material itself.
Have you ever heard about advanced material?
No.
Do you know about advanced material?
Advanced material. Maybe it is something like smart material or anything material that is advanced.
So, do you know about ultra high temperature ceramic?
Ultra high temperature ceramic. I think the substance that withstand a high temperature than usual. This is my only basic knowledge. I don't know the deep one's definition about that. Ultra high. But for me, it's a substance that withstand a high temperature than usual temperature. That's it.
Do you know about ultra high temperature ceramic?
Ceramic I know for floor, but other than that I don't know.
Okay, so you know a little bit about advanced material. So have you ever heard about ultra high temperature ceramic?
Ultra high temperature. I'm not sure about that, but I think it is something like temperature that withstand heat, or like for example, Elon Musk, who are planning to build a spaceship to go to Mars.
Ultra high temperature ceramic is a material that can withstand temperature 2700 Kelvin until 5000 Kelvin. So it is used for spaceship and others that can withstand that temperature. So from the definition that you have given, so how can we know that the material is the ultra high temperature ceramic?
As I said earlier, the material itself withstand with high temperature, and maybe it can conduct electricity better than another material. I don't know. This is only my basic knowledge. Is it?
I don't know. I guess something an element that have high melting point.
Okay, last question. How can we know that material have the properties of ultra high temperature ceramic?
I don't know because I don't do research about that. Sorry.
Thank you. Thank you for your cooperation.
Alright, bye. There are many properties of ultra-high temperature ceramics. Firstly, it has extremely high melting temperature. Let me show you.
Compared to borides, carbide ceramics tend to have higher melting temperatures, typically 200 degrees Celsius or more higher than the corresponding boride.
This ultra-high temperature ceramic can withstand from 2700 Kelvin until 5000 Kelvin.
Next, ultra-high temperature ceramic have high hardness. UHTCs generally exhibit hardness above 20 gigapascal due to the strong covalent bonds present in these materials. However, The different methods of processing UHTCs can lead to great variation in hardness value. Other than that, the properties of ultra-high temperature ceramic is good chemical stability. It is the tendency of a material to resist change or decomposition due to internal reaction or air, heat, light, and pressure. High thermal conductivity. It is ability to conduct heat. Carbide is a material of UHTCs that have a lower value of thermal conductivity compared to boride. Thus, the properties of UHTCs is environmental resistant. This ultra-high temperature ceramic still can withstand even in haze, rain, sunny, and the others condition. Because of that, these materials have been used in aerospace application.
Hello everyone, welcome back to our segment Ultra High Temperature Material, focusing on ceramic. Ultra high temperature material is classes of material that can withstand high temperature from 2700 Kelvin till 5000 Kelvin. A lot of research has been done to figure out which material can fit the properties of ultra high temperature material, and they found that ceramic is the best material, is one of the best material that can fit the properties. But how they characterize this ultra high temperature ceramic? Transmission electron microscopy is a powerful tool to explore microstructure on small length scale to disclose densification mechanism. The author Diletta Siti and Laura Silvestroni from Italian National Research Council on their report entitled Characterization of Ultra High Temperature Ceramic via Transmission Microelectron, they tested ultra high temperature ceramic, namely zirconium carbide, hafnium carbide, hafnium diboride, and tantalum carbide, doped with 50% of tantalum silicide. They discovered various results from transmission electron microscopy image. Let's take a look.
Transmission electron microscopy image 1 showing a typical zirconium diboride grain surrounded by zirconium tantalum bromide solid solution. Next image is the dislocation in solid solution. For this image seen from transmission electron microscopy, it shows crystalline silicon carbide particles within amorphous silicon monoxide phase from which dislocation departs. High-resolution transmission electron microscopy revealed the presence of low-grain boundary lattice mismatch between core and shell, stacking faults in solid solution and amorphous film between two adjacent solid solution, confirming a densification assisted by liquid phase.
Another characterization method that has been found by researchers is aerothermochemical characterization. From few researchers of University of Naples, Federico in Italy, the ArcJet facility has been utilized to test specimens with different shape and different size in a relevant atmospheric re-entry environment.
Tests are typically performed increasing total enthalpy of the flow with several steps corresponding to increasing torch arc power, leading correspondingly to an increase of temperature and pressure.
So let's see what it looks like.
Perhaps the most important part of a space voyage is coming home safely. The spacecraft must survive the extreme heat and friction of re-entry into the Earth's atmosphere. Scientists and engineers create heat shields to protect the spacecraft. But how do they know it will really work? The answer is the ArcJet facility. For decades, this laboratory recreated the heat, gases, and chemistry experienced during re-entry, giving us the confidence to fly, explore, and return home from space. The ArcJet combines heat, the proper mix of gases, and the chemistry that occurs at extreme temperatures to simulate the flow experienced by spacecraft during their fiery re-entry through Earth's atmosphere.
So when you're coming back from low Earth orbit or even the moon, you're coming back at very high velocities. And so from coming back from low Earth orbit, you're on the order of 7 kilometers a second. From the moon, you're coming back about 11 kilometers per second. That's really fast. And so when those vehicles actually encounter the atmosphere, then they're just essentially slamming right into that air. And so that creates a shock wave around the vehicle. And right behind that shock, that kinetic energy associated with the reentry is converted to chemical energy. You know, so you take the basic air, it's mostly nitrogen, about 77% nitrogen, about 23% oxygen. And so what happens is when you go through that conversion process, going to kinetic to chemical energy, what you're doing is you're breaking apart the molecules. And so at first is going to go is the oxygen, then it's going to go the nitrogen. So as opposed to an oxygen molecule or a nitrogen molecule, now you'll have atomic oxygen and atomic nitrogen. And atomic oxygen can be very, I'll call it corrosive, because it really just eats up material. So all that gas on the other side of the shock, on the vehicle side, then encounters the thermal protection system. And so that's how you have to know, well, how does that gas affect that thermal protection system? Is it going to protect the vehicle? And of course, the only way we know how to simulate that on the ground is through these ArcJet facilities.
Because we do not know how a material will behave until it gets in these facilities. There's no analytical equivalent to an ArcJet. We have math models and we have tools, but they require ArcJet testing to benchmark them and to provide the core properties for those tools. So there's a lot of materials that might perform well in a strictly thermal environment, such as blowtorch, but will not perform the same in an ArcJet or in flight because of this chemistry of the flow field.
So the basic operation of the ArcJet is to simulate the reentry environment. The nuts and bolts of it is you want to take gas and just take it to a very high energy level. And the heater is the workhorse of the ArcJet facility. So all the components come together to make the test work, with high pressure water cooling for the cooling of the segments, to the test gas, the nitrogen and oxygen, to the electrical power, and then into the vacuum system for testing the material. Okay, so when we receive a model, typically the models come with thermocouples already attached. And then in the test chamber, we have 2 hydraulically actuated sting arms. So we would establish our flow field, and then the model is on a sting arm, we rotate into the flow, we would test it. And then we would rotate it out of the flow field. So on that sting arm is where all the data hookups are. So we would run that to our data system. During the test, we get all kinds of additional data. We would test these types of ablators, typically up to 3,000, 4,000 degrees Fahrenheit, even higher. We would test them at very high temperatures for different types of trajectories, primarily for the lunars, what gave the highest types of heating rates and correspondingly the highest temperatures of the surface of the model. For a ISS type of reentry, the heating rates are a lot lower, so we're talking about 2,000, 3,000 degrees, but for a lunar type, very ballistic type of reentry, you're about 4,000 degrees, even higher than that.
Synthesis from elements. Reaction between elemental boron and metal powder is the simplest route to produce boride powder. It can have excellent control on the stoichiometry of the resultant boride. Although this route results in pure zirconium diboride and hafnium diboride but cannot be employed for industrial production because the starting materials used are expensive. This route can be exploited to get dense shapes of borides by hot pressing or spark plasma sintering of mixed powder, metal and boron, if the reaction with dye is avoided. To avoid any reaction with the dye, the graphite dye is coated with boron nitride. This route can also be used to prepare diborides using self-propagating high-temperature synthesis, SHS. SHS is a technique that uses the high exothermic energy of chemical reactions to generate high temperature required for the reactions. Benefits of SHS: high purity of the products, short process times, typically of the order of few seconds or less, low energy consumption, limited to the ignition step, low cost of the experimental apparatus. Boride powders formed using SHS have better sinterability due to the presence of lattice defects. These lattice defects are created by the rapid heating and cooling during SHS process. However, rapid heating rates can also cause incomplete reaction. 1. The formation of non-equilibrium phases. 2. The formation of stable oxides. 3. The retention of large amounts of porosity, 50%. Gash et al., 2004. Molten salt electrolysis. Various metal borides can be prepared by molten salt electrolysis. Fraser et al. 1975, have deposited zirconium diboride on nickel cathode from zirconium oxide and boron trioxide dissolved in molten cryolite at 10-20 degrees Celsius. A series of nickel boride diffusion compounds were also noticed by electron microprobe analysis. A graphite crucible was used as anode. The zirconium diboride deposit was found to be scaly or dendritic and was usually non-adherent. Devyatkin, 2001, has also obtained ZrB2 on nickel cathode from cryolite alumina melts containing zirconium and boron oxide. Synthesis by polymer precursor route. A processable polymeric precursor for boride synthesis can be obtained by dispersing a metal oxide in a boron carbide polymeric precursor. On heating, the mixture results in either in situ generation of boron carbide and carbon, followed by reaction to produce the boride, or direct reaction of the polymer with the metal oxide to give the final boride product. The key requirements of the polymer component are given below. 1. It should be stable. 2. It should be processable, and 3. It should contain both the boron needed to form the metal boride and carbon to aid in the removal of the oxygen. Dinitrile polymers satisfy these criteria and can be prepared in good yield from the condensation polymerization of decaborane with dinitriles. Su, 1991, have obtained the polymer precursor by dispersing zirconium oxide into decaborane dicyanopentane polymer. Subsequent pyrolysis of the precursor at 1450 degrees Celsius yielded crystalline zirconium diboride.
Densification is the process from powder of UHTC material to a required dense shape. Densification of UHTCs is extremely difficult due to their high melting point, strong covalent bonding and low intrinsic self-diffusivity. At lower temperature, surface diffusion and evaporation condensation mechanism are favored, which results in mass transfer without densification. At higher temperature, exaggerated grain growth takes place which results in poor mechanical properties. In order to achieve the densification, there are 3 ways. 1. Use an additive which forms a liquid phase at sintering temperature. 2. Increase the surface energy of powder by removing the surface oxide layer. 3. Increase the defect concentration by mechanical activation. Several additives have been exploited to improve the sinterability and properties of zirconium diboride and hafnium diboride. Silicon carbide is the most popular additive as it enhances densification, prevents grain growth and also provides oxidation resistance to the UHTCs. Silicides metallic additives assist in densification by liquid phase sintering, but they may not be suitable for high temperature application due to lower melting temperature. There are 5 classification of the densification process. 1. Pressureless sintering. 2. Hot pressing. 3. Spark plasma sintering. 4. Microwave sintering. 5. Laser sintering. Pressureless sintering is a very simple and economic technique to produce dense shapes of ceramic materials. This operation is carried out in 2 steps. 1. Green compacts with sufficient handling strength are prepared by uniaxial die compaction or by cold isostatic pressing. 2. These green pellets are fired at required temperatures in controlled atmosphere. Firing can be done in an induction furnace or resistance heating furnace. Figure 1 shows the induction furnace. Pressureless sintering is preferred to fabricate near-finished components, which will drastically reduce subsequent needs for diamond machining. Full densification of monolithic borides requires very high temperature and longer duration. Metals, carbon, carbides, and silicides have been used to enhance the densification. Addition of carbon assists in densification of borides to a density of more than 95% ρth at temperature around 2000 until 2100 degrees Celsius. Metals and silicides improve the densification by forming liquid phases during sintering. Pressureless sintering may be useful for fabrication of shapes where high density is not required. In hot pressing, temperature and pressure are simultaneously applied to the powder compact. Heating is usually carried out externally using graphite resistors and the pressure is applied hydraulically. Figure 2 shows hot pressing schematic. Under the application of pressure, the contact points between particles are at very high stress and thus diffusion gets increased at those contact points. Particle size influences the density and microstructure of the hot-pressed compacts. Before hot pressing, UHTC's powder is milled by ball milling or attrition milling to obtain a powder of less than 2 micrometer size. The milled powder is filled in the graphite die and then heated to required temperature in vacuum or argon atmosphere. When the die temperature is reached to desired temperature, uniaxial pressure of around 30 to 40 MPa is applied. Hot pressing temperature, pressure, heating rate, atmosphere, and holding time affect the properties and microstructure of the densified parts. Hot pressing method is limited to simple shapes while complex geometry but cannot be fabricated using this technique. Sintering additives such as metal, silicides, carbide, nitride, and oxides helps in bringing down the hot pressing temperature and results in near theoretical densities. The selection of sinter additive is very important as these additives also affect the mechanical, thermal, and oxidation properties of UHTCs. Spark plasma sintering, SPS, is a novel technique, which gives dense shapes of UHTCs at a lower temperature at shorter time compared with conventional techniques. In the SPS technique, a pulsed direct current passes through graphite plungers and dies simultaneously with a uniaxial pressure. Figure 3 shows the schematic diagram of spark plasma sintering process. The fast heating through the range of 1500 until 1900 degrees Celsius reduces the time over which coarsening may occur, and thus the grain size of SPS sintered material is fine. SPS is suitable technique for the preparation of nanocomposites as no grain growth takes place in this process. In microwave sintering, heating of powder compact is achieved by absorption of microwaves within the material to be sintered. Some of the materials do not absorb the microwaves at room temperature, but they absorb it at higher temperature. The addition of a microwave absorbing second phase to ceramics that are microwave transparent can greatly enhance the interaction of the system with microwaves. Microwave sintering has the advantages of uniform and rapid heating since the energy is directly coupled into the specimen rather than being conducted into the specimen from an external heat source. Generally, enhanced densification and finer microstructures have been reported for microwave sintered materials. Microwave sintering resulted in the densification of the composite at lower temperatures. Laser sintering is a rapid prototyping technique that prepares dense shapes by sintering the powder layer by layer. It is a novel technique to fabricate cladding layers as well as freestanding 3D structures of UHTCs. When the powder surface is irradiated by the laser beam, it absorbs energy and the temperature increases, resulting in necking, grain growth, partial melting, and densification. In this technique, contamination is minimal as it is a non-contact process. Laser power, beam spot size and scan speed are major processing parameters in laser sintering. Sintered objects have densities larger than 95% of theoretical values and have micro-hardness values up to 16.0 GPa. This technique seems capable to create complex structures or repair UHTC objects and thus would be especially beneficial in saving time and reducing overall cost.
Now let's hear about application of ultra-high temperature ceramics materials, UHTC. First of all, application of ultra-high temperature ceramics materials, UHTC, is hypersonic flight. What is hypersonic flight? Hypersonic flight is vehicle that fly through the atmosphere below 90 km at speeds above Mach 5, 3,836 miles per hour. Many worldwide nations have built this hypersonic flight, such as Russian MiG-41 jet, Russian, Air Force X-15 aircraft, USA, State Route 72 scramjet, China, NASA X-43 a hypersonic jet. Part of components that use UHTC in hypersonic flight are edge and cone of jet flight. UHTC can conduct energy through the material and re-radiate it through cooler surface. Most common materials of UHTC for aerospace ship are diborides of hafnium and zirconium, which required chemical structural stability at extremely high operating temperature. Secondly, control rods. What is control rods? Control rods are used in nuclear reactors to control the fission rate of uranium and plutonium. Control rod also used to absorb neutrons so that controlling reactor core can be slowed down or stopped completely by inserting the rods further or accelerated by removing them slightly. Essentially, control rods provide real-time control of the fission process, ensuring that it remains active while preventing it from accelerating out of control. For example, uranium-235 fission releases 2.5 neutrons on average, but only 1 neutron is needed to sustain the nuclear chain reaction at a steady rate. The control rods will absorb these extra neutrons in order to adjust the power output of the reactor. When inserted the standard amount, their position is at criticality and the power output remains the same. If the rod is pushed, the number of neutrons decreases along with the power output and the reactor is below criticality. The opposite is true if the rods are pulled out slightly as fission goes beyond criticality. Control rods are made of UHTC materials which are ZrB2, zirconium diborides, HFB2, hafnium diborides. Thirdly, is rocket propulsion. What is rocket propulsion? Rocket propulsion is process that use force to move a rocket off the ground to atmosphere. There are two types of rocket propulsion systems, liquid propellant and solid propellant. The solid propellant is usually arranged to protect the motor case from heating. Most modern propellant charges are formed by pouring a viscous mix into the motor case with suitable mold fixtures. The propellant solidifies by polymerization and the mold fixtures are removed, leaving the propellant bonded to the motor case with a suitably shaped perforation down the middle. Liquid propellant systems carry the propellant in tanks external to the combustion chamber. Most of these engines use a liquid oxidizer and a liquid fuel, which are transferred from their respective tanks by pumps. The pumps raise the pressure above the operating pressure of the engine and the propellants are injected into the engine in a manner that assures atomization and rapid mixing. The principal requirement for a nozzle that use solids and liquids propellant are they able to produce a supersonic flow of the exhaust gas from the combustion chamber pressure to an exterior pressure. Components in rocket that use UHTC are motor and nozzle throats. These are the example of the nozzle throats rockets. As we can see, TAC and HFC are used in making of nozzle throats.